Okay, welcome to BITS Pilani, Hyderabad campus, and to the course of Physics and Modeling of Microelectronic Devices. So I am Dr. Surya Shankar Dan, and I'll be your instructor for this course. So before we begin this course, I'll just share with you some of the logistics involved with this course. For example, the videos of each of these classes, so whether it is a lecture or tutorials, laboratories, whatever, we are all going to post it here, okay, under these videos. And also I'm going to share with you that YouTube channel link. Okay, so this is empty now. It is going to get populated as we go along. These individual videos will also be here, but I will strongly recommend that all of you should kind of what is that called, subscribe to this particular YouTube channel, okay, so that whichever post I make, you will always get an intimation for that. Okay, so this is the Google Meet link which we are using. So all these details will be available in the classwork tab of your Google Classroom. Okay, the stream is only for the basic announcements and stuff, so do not pay much attention unless you require it. But mostly the materials will be uploaded in this particular tab. All right, then the schedule has been shared with you. These are kind of self-explanatory. So you need to get bothered only about the PMMD lectures and the PMMD practicals. Okay. So I did not want to spend time and removing this ADVD entries over here. That's the BTech course which I am taking, analog and digital VLSI design. So this is for the higher degree. It is PMMD. Okay. So what else? Yeah. There is a handout which is probably shared. I do not know if it's available with you. However, this is what concerns you the most, the course evaluation part, okay, here, and the references. So usually, I mean, I would be following this particular book, okay. This is the book which I studied in IIT Bombay as well as in IIC Bangalore, okay, during my kind of graduation and PhD. This is kind of a slightly more advanced book, okay, that is Civiris, but that concerns only MOSFETs. So if you want to do a major in devices, then it makes sense. Mostly, it's kind of an overkill for this course. The Jean-Pierre Collange and Collange, they are French people, so it's not Collinge, it's Collange. That's how you pronounce in French words. Okay, so Jean-Pierre Collange, so he is the inventor of SOI technology, okay, silicon on insulator. So whatever you see, every device in the world today are SOI. So those portions I'm going to study and teach from this book. And Muller and Cummins were my professors in MIT. So I'm just putting a reference. Okay, so these are the basic references. These are the primary references for this course particularly. So in case you find something difficult over here, I can always refer to these basic references for your BTech level. So I expect you to know devices at this standard. Okay, that brings me to a very, very important concern, that is basically related to your background. I'll come to that in a minute. So these are the basic references. Probably most of you who are coming from ECE background, they must have studied this book of, let us say, Streetman or Nieman and all that, right? So these are kind of that level itself. So these are very good. So Robert Peer, okay. I'm sorry. I should increase the fonts. So Robert Peer, for example, was the textbook in IITs at the BTech level. Okay, Torrending was the textbook in the IITs at the MTech level. So I'm just following the IIT standards here. Okay, so Chenming Hu is the person behind the BISIM model, which is kind of the industrial standard for the device designs, circuit designs in industry. So that's why I put it here. Okay, these are advanced references specifically if you want to do a major in this. So Those of you who want to pursue a PhD later on, or you want to pursue higher studies, then you can basically get into this. But only very few instances will be there where I'll essentially refer to these. I'll mention those in the class. Okay, coming back to the evaluation scheme, I do not kind of encourage, or I do not personally believe in taking more number of quizzes and class tests, because in that process you are essentially going to lose the, I mean, you will lose the class hours for taking the tests. On the contrary, I will put more effort. I will put more emphasis in your, let us say, laboratory evaluation here. Okay, instead of laboratory evaluation, I could have made it quiz or something, but I would prefer to do it, because this laboratory evaluation, in each of this laboratory evaluation, you are going to develop the models on your own. Okay, so in the process, you are going to learn a lot about the device performance, device characteristics, rather than giving you class tests where you simply mug up some concepts and you just write it down. Because later on, as you will note, that your projects in these courses will help you much more in your placements rather than kind of lecture kind of classes. Okay, and literature review will be your first introduction to how to do kind of, how to know about a topic, some new topic, based on the technical literature. Okay, difference between technical literature and textbooks. In textbooks, for example, this Torrending and all the books, Streetman and Banerjee, whatever you have studied, they are essentially, I mean, they are writing in much more, uh, they write they write in a much more detailed way. So in this case, what we shall do is, in literature review, we will be discussing about one topic in which you will have to figure out what is the latest on that topic. Okay, so basically that will be your first introduction to it. We will come back to this later, and in case you find any difficulty over here, we can even change this, so there is no issue with that. For example, this is usually not there in most of the handouts. Okay, I have put mentors because they are your seniors. Okay, they have been working with me for the last 1 year. So Anish, Srikant, Pawan, Shivam, and Ajit, they have all been placed in excellent companies and all that. So what I will recommend you is that they are anyway staying on campus, right? So your seniors are there. So I would always recommend you, like, if you are having any problems, okay, then you can contact them. Okay, mentors. And then any technical issues you face, me and my PhD scholar, Shomi Shaha, both of us are here to help you out for the technical details. Okay, excellent. So now we will just get back to, oh yeah, sorry. Another thing about your background. In fact, that is one of the things which I essentially mentioned here. Just a sec. Yeah. Okay, how many of you from the electrical background? I have highlighted them based on your response. Okay, Rishabh, can you please open up your microphone and tell? Yeah, okay. You just throughout this semester, I'll tell you, I mean, in my courses, it is a very, very informal and friendly atmosphere. Okay, so I want you to interact straight away. You open up your microphone and start speaking. That is an easier way, faster way of doing it. All right, so Rishabh is here, Isha is here, Vivekanando is here.
Yes.
Yes, good. Sohail, so now my questions to all of you who are from the electrical background. Okay, Swagat Mohanty is also in electrical, right? So have you studied anything in the like devices, concerning devices in your BTech?
Yes, sir.
Hello, who is this? Anisha?
Yes, sir.
Yeah, Rishabh and all. So which textbook did you study and all?
No, sir.
You have not studied. Who is this?
Sir, I'm Rishabh.
Rishabh, you have not studied devices in your BTech.
No, sir.
Okay.
There- So there
So
were a little bit introduction about devices like in analog.
Okay.
Analog electronic circuit. Like,
Analog
Sir,
yes.
we have studied digital electronics and analog
Analog
electronics, sir.
electronic circuit.
Okay, so those digital and analog electronic circuits you have studied as a CMOS approach or the device, CMOS designs.
Sir,
CMOS
sir,
circuit.
No CMOS,
we
sir.
basic
Please
sir
tell me.
we basically studied, sir, BJT diodes and we
Op-amps and all.
transistors, op-amps transistors, sir.
So op amps are black boxes, right? So you
Yes,
have
sir.
done BJTs.
Yes, sir.
BJT is the technology which was driving Second World War. Okay, so that is
Okay.
100-year-old technology. BJT is obsolete. So we are
Excuse me, sir.
studying. Yes, please tell me. Who is
Yes,
this?
sir. This is Sohail, sir.
Sohail. Yeah, please tell
Sir,
me.
I would like to just add that we have studied only like formula-based related electronics,
Oh,
not conceptual devices.
okay.
Mhm.
All right. So formula based essentially again for BJTs, huh?
Yeah, BJT and a little bit of CMOS also.
Okay, great. Um, to be very honest, like we have to of junctions. Okay, so that means as we go along, we will explain in much more details later on. For example, any kind of devices which you see, they will essentially have only two phenomenon. Okay, fundamentally there are only two phenomena. One is the field effect phenomenon, the other one is a junction related phenomenon. Okay, so if you can understand the junctions, that will essentially answer all your queries regarding devices which are junction based devices. Typical examples of junction based devices are PN diode, BJT is, all of you know, back to back diodes, right? So basically those are all junction devices. Then let us talk about heterostructures. They are also junction based devices. LEDs, again, light emitting diodes. That's also a junction based device. Lasers, light amplification by simulated emission of radiation. So laser diodes, those are also junction based devices. Again, on the other hand, there is like for example, metal semiconductor junction. Again, MIS diode. These are all junction based. On the flip side, we have got field effect devices. Typical examples: MOS capacitor. Remember JFET. Many people make it a mistake. Like JFET, although there is a field effect, but still it is kind of a junction phenomenon. So MOSFET, for example, MOSFET is a field effect phenomenon. Okay, so MOSFET, gated diodes, MOS capacitors, so SOI technology, FinFETs, tunnel FETs, these are all field effect devices. Okay, so we are going to learn them. Now, the main focus of this course will be primarily MOS devices or field effect devices. Okay, we are not going to spend more time on junctions. Okay, because junction is totally backdated. Whatever portion of junctions we will be covering in course will be primarily just to make justice to the syllabus of this course. ठीक है, ऐसा नहीं हो, ऐसा होना नहीं चाहिए कि आफ्टर एग्जाम, आफ्टर द कोर्स इज ओवर, कोई आपसे पूछा आपने बीजेटी नहीं सीखा, तो सूर्या सर ने क्या सिखाया, something, I mean those kind of things should not happen. Okay, so we will just study that like that itself. But in this 4 month, this is probably 4 month long semester. Out of this 4 month, you will find the first month. Within the first month, we will be going all the way into devices proper. So we will begin with some of the quantum mechanics, like the very basics about the semiconductor material science, because without that, you will not be able to appreciate what is going on inside the device. Okay, some very, very basic things. I can essentially spend several, 3 or 4 semesters on semiconductor physics, but that is not the objective of the course. But still, we will be going through around three weeks or so on vector physics, so that you can better appreciate the devices. So after that, we will directly go into the junctions, and then practically 3 months of this course will be dedicated for MOS. Okay, because that is where your job opportunities are. All right. So I have spoken roughly to, many of you from the electrical background. Okay, those of you who are in the triple E background. Okay, so let's check out who are in triple E. Hitesh, Ranit, there are many, right? So in the triple E background, you have got some idea about the devices. You have learned that in the electronics part, right? Hello. Anyone from the triple E
Hello.
background?
Yes, sir.
Yes. Do you have some kind of basic idea about devices in your BTech?
No, sir. That was not in our syllabus, sir. EDC subject was not there.
Okay. अगर EDC नहीं है, then how did you even clear your gate or BITSAT?
Sir, I gave the exam in electrical domain, so
Okay, 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 fine.
EDC was not our syllabus.
Okay. All right. I think EC people are aware of this. Fine.
Yes, sir.
Okay. So what we will do is we are essentially going to go through the various topics here. And I will try to make this course as much self-contained as possible. However, you will find that I will be skipping many topics. So I will never claim that this 4-semester course is a 4-month semester-wide course is kind of complete in itself. No, not at all. Okay, I am going to skip many topics here which are not that much relevant for your placements. Okay. So my focus of this course will be completely for your placements and your further positions in the higher studies. Okay. With that in mind, let us begin with the course. Anybody having any questions until now?
Yeah,
Yeah.
good afternoon, sir. This is Shreya.
Yeah.
I'm having an instrumentation background, but
Okay.
even we didn't have a proper subject on devices or its physics. So yeah, I want to add on that.
Yeah. The only thing I'll tell you, if like I guess most of you are interested in getting placed, right?
Right.
So as far as your placement situations are concerned in India, all the VLSI companies are looking for circuits background, and that too ultra low power circuits.
Okay.
So the devices perspective which we are going to teach in this course will be primarily oriented towards the understanding of the modern devices, the devices which is being operated in your smartphones, for example. Okay, so that when you are essentially going for an interview in Qualcomm, they will find that you know what they require. Okay, so that is the perspective of this course. So in the process, I'm going to, as I said, I'm not going to do justice to BJT. Okay, so I mean, if you really require, I can essentially go on and on on BJTs, obsolete devices, but quite honestly, it's not worth my time. It's not worth your time. Okay, so that's why I mean
Sir,
that.
do we need to start with? Do we need any EDC prerequisites as a prerequisite? We have
Yes,
to
actually, it
like
is there. In fact, in the document which I shared with you,
yeah.
just a sec. Evaluation, yeah, here itself. If you notice, I have written it, but like prerequisites for the course includes EDC. Okay, EDC. Okay, but essentially what we will do is, in case you are not aware of many stuff, some of the stuff which I am teaching, then you can of course point it out. I am going to go to length to make your concepts clear. Okay, and
Sure.
these concepts will be essentially geared towards understanding the circuits, because in the interviews you will be asked questions based on the modern day technology on the devices, as well as how to design circuits with them. So I mean, these two combination of the courses has been working wonders, to be very honest. This PMMD I'm teaching this semester. Next semester I would be able to teach advanced VLSI design. Okay, so the who is teaching VLSI design this time? Sayed sir?
Sayed sir, yes.
Yeah. Okay. So based on what Sayed sir is teaching this time, so next semester we are essentially going to go much deeper into the VLSI designs, where we will be incorporating the modern devices which we are going to learn in this semester, incorporate that in the circuits, and essentially you will be at par with the requirements of the industry. Okay, so that is my target, so that within these 2 semesters, as I said, I mean, you practically have just 1 year, that is 2 semesters before your placements begin. Okay,
Yes.
so this semester we are going to learn about the devices which are kind of the active components of the circuits which we are going to design in the next semester. So in your placements, you will be asked questions primarily on the circuit level, ultra low power circuit designs, VLSI designs, and at the device level, sometimes, for example, this time Micron was asking a lot of questions on electronic devices. TI, for example, they were asking questions on electronic devices. So that often happens. This time Intel did not come until now. I do not know. I mean, all the students are placed in your senior batch. So if Intel comes, they will not have any students left. So in your batch, probably Intel, if they come, they will essentially be interested in devices a lot. Okay. So anyway, we will just go into this as we go along. Okay.
Yeah.
All right. So here, like compared to the previous few years, I have taken a different standpoint. For example, in the previously, what I used to do is I used to derive everything from scratch on this whiteboard, okay, on this white sheet of paper. So instead, I have done the derivatives, all the derivations over here, and this is getting video recorded, as you all know, and this I will be uploading on YouTube. So the main point will be I'll be using two boards like this. In one, I will be doing the explanations. In the other, here, you will find the derivations and everything, mathematical derivations and all are done over here. So that when I will be explaining and going back and forth with the mathematics, I will not spend time on doing the mathematics here. Okay, so it will save our time. Whereas you will have ample time in your hostels to basically go through the mathematical derivations, which will help you better. Is that clear, everybody? So I do not want to waste time on doing the algebra in the class. Okay. I think that is good enough as an introduction. So we will begin with quantum mechanics in this course. Okay. Now, quantum mechanics is kind of an ocean. Okay. But we will study quantum mechanics only to the extent of understanding the formation of solid state. Okay, please understand that. So that means quantum mechanics can be used to explain kind of, I mean, except I think long range gravity, everything, every phenomenon in this whole universe is explained by quantum mechanics. We are not going to go into any of those. We are only concerned about understanding why semiconductors behave the way they do. Okay, why semiconductor is a semiconductor, why metal is a metal. Okay, why suddenly silicon has a band gap of 1.12 electron volts at room temperature, of course. Okay, so essentially those are some of the fundamental questions we are going to answer using quantum mechanics. Is that clear? So our objective of quantum mechanics is just to understand how and why. And by the way, in semiconductors, we are essentially referring to silicon here, because silicon is the material for industrial material as of now for electronics. So that is our objective. Now, to begin with, let us begin with understanding the quantum mechanics from just VLSI perspective. Okay, another thing I must tell you at the very beginning, this session is actually a lab session. Okay, but since this is the first lecture, so I wanted to begin with a little bit of introduction and quantum mechanics here, so that next week we will begin with our lab assignments. Okay. All right. Fine. So now let us understand first a wave equation. ठीक है? आप लोग सब quantum mechanics वगैरह सब भूल जाओ. Just forget about all quantum mechanics, solid state. Okay. For Qualcomm, I need to know devices and circuits. सब कुछ भूल जाके. All I'm asking you to do is just remember the very, very basic wave equation. Okay. So what is a basic wave equation? We can write this y as a function of x is equal to a sine omega t. Okay. Very simple. अच्छा, इनमें से आप बताओ इनमें से, like what does this a indicate? We know everyone this is an amplitude. Amplitude. Right? Amplitude. Excellent. अच्छा, इस bracket में जो है ना, what is that? That is the phase which I will as the phi. Okay. Now, if you notice that whenever we are writing this form, this is nothing other than the imaginary part of the wave equation which we can write like this. Yes or no? Because remember, phi theta is equal to cos theta plus epsilon. Very basic first year mathematics problem. Okay. So this is the imaginary part of this. Now we could have also written this as a cos omega t, which will be simply the real part of e to the power I theta. Correct? Yes or no? Okay. Now the point is, both of these functions, sine and cos, these are sinusoidal functions. Now this phase part, it does not affect the amplitude. Now it turns out that the intensity of this wave, okay, depends on this amplitude alone. Okay? This amplitude is the only factor which will influence the intensity. Okay, whereas this phase factor, that will essentially have one phase advance or the phase lag. Okay, so all we can do is, let us say here, okay, we can actually add another part which is essentially a space dependent part. Remember, omega t is basically the time dependent factor. वो हम लिख सकते हैं कैसे? kx. We can say this kx. Very simple. You might be thinking, okay, this is so silly, but we will soon try to understand it from quantum mechanics perspective, and things will become complicated very, very soon. Okay. I have not done any quantum mechanics here. This is simply wave theory. Okay, electromagnetics, microwaves, even AC signals are also like that. So now, one very important part to understand. Whenever we have plus here, suppose I can put a plus minus here. What does this plus or minus indicate? Open up your microphone and start answering.
Yes.
फेज शिफ्ट. ओके, प्लस एंड माइनस में फेज लैग कौन सा है, फेज एडवांस कौन सा है?
Plus means lag and minus means lead.
Place plus is phase advance and minus is delay.
Okay, so now my question is, suppose I put the plus mark here, can I put it there? यहाँ लिख सकते हैं क्या?
So that could result in minus t.
Exactly. What is the meaning of that? That will result in minus t. Very good. You have hit the bullseye. But क्यों? उसका problem क्या है?
Sir, signal will reversal.
हाँ. So that means what? In any physical phenomena, that will always go. I mean, there is a technical term for this. Physics says there is called the thermodynamic arrow of time. That means time is always in one particular direction. Okay, so this time over here, this factor t, you cannot put it as negative. That means whatever phenomenon which you are observing in nature, that is always going to be in the particular direction of time advance, not time lag. Okay, mechanically, if you are essentially drawing an axis, for example, here, sorry. So if you are drawing an axis, okay, so you have started making an observation, it is always going to go in this direction. वो negative t direction में कभी जा ही नहीं सकता. Is that part clear? So even though you can have a plus minus here, you can never have it in the front. समझ में आ गया? Because you are going to have a negative t in that case. Correct? With this very basic idea, let us understand quantum mechanics from this perspective. Okay, so what is a progressive wave? A progressive wave is what I wrote over here. Notice one very fundamental thing which we have explained. This omega t is having a plus sign over here, whereas this kx part is a plus minus. It can be plus or minus, okay? Amplitude and all. Now, can you please switch off the microphone? Unless you are not talking, please switch off the microphone. Yeah, thank you. Because this is getting recorded, so later on when you are revising this, you are going to have that noise. Okay, so now if you notice, we are going to take care of some of the very basic concepts like Planck's hypothesis, de Broglie's formula and all that, which you have studied in your school itself. Okay, so that is E equal to h nu. Nu is the frequency, h is the Planck's constant, and from there, very basic derivation gives you h cross omega. Then P is equal to h by lambda, de Broglie's formula. Both of them won the Nobel Prize for the small equations. E equal to h nu, Planck got Nobel Prize. P equal to h by lambda, de Broglie got Nobel Prize. Okay, so P equal to h by lambda, and essentially you end up with h cross k. Fine. So now, when we are essentially putting this in this formula, what happens? That we are going to replace y by a y in Greek letters. In Greek letters, y is basically psi. So psi xt is equal to a e to the power. Instead of writing psi sign, I can always use exponential as we have seen previously, right? Let us see. Yes, we have already seen this previously. So now, instead of k and omega, I have just plugged in e and p. Okay, very simple. Nothing special about it. And as I told you previously, that this a factor, the amplitude, essentially the square of the amplitude, essentially gives you the intensity, right? So the intensity for this particular wave function is basically given by this one. We will see why it is called a probability and all that later. Okay, this is some quantity, let us say. It essentially represents the probability that you can essentially find that particle in that particular location. Okay, now once you are essentially taking a derivative of x, derivative of psi with respect to x, and the derivative of psi with respect to time t, you will essentially end up in these two equations. Okay. By the way, in my course, you do not have to memorize any equation. Whatever equations are necessary for solving the problems, even in the exams, those equations will be either provided to you, or I will allow you to bring one A4 sheet full of formulas. Okay, you can write whatever you want on that, whatever formulas you want on that piece of paper. All right. So once you have got these equations, now what we shall do is we will try to equate these factors, these parameters, in the basic condition for total energy of the quantum particle. Now, those of you who are coming from a physics background, I don't expect any one of you. This is called Hamiltonian. Okay, I am not using some complicated terminologies here for the benefit of the students. So this is basically the total energy of the particle. Okay, so how much will that be? Kinetic energy plus potential energy. Okay, so potential energy. Well, how do you define potential energy? Potential energy we have seen from our school days. Potential energy is essentially the energy of the particle because of its position, right? So here Vx, which is the potential energy of the particle, this is actually a function of x here. ठीक है, यहाँ पर हमने t नहीं लिखा है. ठीक है, please note, because by fundamental definition of potential energy, it is a function of the position of the particle. ठीक है ना? And half mv square, v is the velocity of the particle. So essentially, this is the energy of the particle because of its state of motion. Motion है तो velocity रहेगा. Okay. Now P is equal to mv. Right? So from there we get m square v square by twice m, that is p square by twice m. Okay. So now what we will do is, if this is an equation which we are having, e p square by twice m plus v, and then we will apply both the left hand side and right hand side, we will apply to the wave function. What happens? You will essentially end up that E psi is essentially given by this equation here. Correct? We have just derived it. Okay, there is nothing special out here. And P square psi is given by this relation. Okay. So I have done all the detailed calculations here. So I do not want to spend time on this in the class. So हमने यहाँ पर क्या किया है? We have once we have obtained these expressions, then we will replace E psi by this P squared psi over here with this. So this is the fundamental derivation of the Schrodinger equation. You will not find this in most of the textbooks. Okay. Of course, if you go to a physics major person, they will say, no, this is not a very accurate way of proving Schrodinger's equation. I understand. But this is good enough for your understanding as a VLSI engineer. Okay, this is good enough for you. So in the interviews, if somebody asks you, okay, throughout this course, I'm going to give you tips for the interviews. If somebody asks you in the interview, like, what is the origin of Schrodinger equation? You'll have to say energy balance. Okay, so the total energy of the particle is equal to sum of the kinetic energy plus the potential energy. Okay, and then we have simply incorporated the progressive wave equation and replaced the P squared psi and E psi operators, and we in the Schrodinger equation. Okay, everybody, that's good enough for your understanding. Now, this Schrodinger equation, what we have derived from scratch from our fundamental principles of energy balance, now we want to find out like what can we do out of this Schrodinger equation. Okay, remember this Schrodinger equation is essentially dealing with the subatomic particles, right, electrons, whatever. So now when we are trying to apply this Schrodinger equation to the electrons under various boundary conditions, different situations, you will suddenly find that you are ending up with metals. Sometimes you are ending up with semiconductors. Sometimes you are ending up with insulators. So we want to understand that. Okay, so that is the whole perspective in the very beginning sessions of this course. Okay, now what we'll do is notice that there is a time factor here. Okay, so this is a time dependent form of Schrodinger equation. Very simple. So यानी कि यहाँ पर psi जो है ना, this symbol. So by the way, there is a difference between this and this. This is the capital psi. This is the capital psi here, and this is the small psi over here. Okay. So what we will do is these are the capital psi, which is a function of both x and t. Again, I must repeat that this is the simplest situation which we are explaining here, because I do not want to go into any of the depths of quantum mechanics. So this x is essentially in one dimension. So if you can understand one dimension, the other two dimensions is basically you can simply extend this discussion for the other axis as well. Okay. So now I will ask you a fundamental question. Let's see. There is a very interesting method called method of separation of variables. Okay. Now my question to all of you is, when is this method of separation of variables applicable?
In differential equations.
अच्छा, कोई भी differential हो जाए?
More than two variables.
Sorry?
More than two variables, like x and t, both are independent.
Yes, very good. This is not independent means basically what I think it was Naresh. I don't know. So what we are essentially looking for is that the two dependent variables over here is x and t. Sorry, two dependent variables here are x and t. The method of separation of variables is applicable if and only if, please note, that the influence because of x and the influence because of time t are mutually exclusive events. Okay, so that means I'll write over here x and t, this psi x and tau t. So what Naresh was, I don't know, was it Naresh?
Siddharth, sir. Siddharth.
So what Siddharth had said, that x and t are mutually exclusive. No, because mutual x and t are independent variables. वो तो independent होना ही है. So the influence of x is psi x, influence of time t is tau. If psi x and tau are mutually exclusive, that means the variation of capital psi x because of time t is independent of the variation in psi x because of x. ठीक है, इसी को हम लोग technically we will call this as, in mathematically or technically we will call it mutually exclusive events. ठीक है, we will use this concept many times. Okay, so these are mutually exclusive events. Notice this is similar to the situation which we saw in case of the probability theory in BTech. We have seen, right? उसमें क्या होता था? You have got two die in your hand. Okay, so what is the probability that you get 6 in your die? 1/6. But what is the probability you get 2 6s in both the die? 1/6 into 1/6. That, why are we getting it? Because the occurrence of 1 6 in one of the die is completely independent, okay, of the other die is getting another 6. Yes or no? Understanding, right? So that means 1/6 into 1/6. So that means you are essentially making a product of the two probabilities because they are mutually exclusive events. Similarly, here also is the same thing. Okay, so we are understanding it in a much more details. Now you can clearly understand. So in the textbooks or somewhere you will find using the method of separation of variables. Acha, kyun? So now my question would be, in the interview somebody can ask, so what is the basic condition that you can apply method of separation of variables? This is the condition, that the influence of each of the individual independent variables, not x and t. Okay, individual independent variables are x and t. X and t to independent hona hi hai. ठीक है ना? Okay, so what is interesting is the variation, the function due to x, that means influence of x and the influence of tau are mutually exclusive. Okay, excellent. So once you understood this method of separation of variables, then rest of the things are very simple. यहाँ पर we will just put this product over here. Then basically this del psi del t becomes, as it is mutually exclusive, so psi x is in of time t, तो वो derivative के बाहर आ जाएगा. Similarly over here tau will come out because it is independent of x. Okay, and then you will essentially end up in this relation. Now comes another very interesting part. Notice that if we arrange it like this, हमने क्या किया है, यहाँ पर ये psi t है ना, this psi into tau we have simply divided on both sides. Cool. So on the left hand side it becomes IH cross 1 upon tau d tau dt is equal to, these are all psi or basically only x dependence, and on the left hand side it is only t dependence. Okay, now let us understand this very carefully. So you are essentially trying to equate two sides of an equation, okay, in which one side is totally time dependent and the other side is dependent only on x. It is not dependent on time t. Here it is not dependent on time x. So that means on space x. So that means if this is an equal, it has to be for a specific constant which is independent of x and t. हम यहाँ पर constant बता रहे हैं, but remember this may not be constant. It is technically it is independent of x and t. That's it. Okay, it can be a variation of z, for example. Okay, because z is not here. Okay, na? The only thing is that it is independent of this t. It is independent of x dependence. That is the reason why. That is the only reason why it is a. I am calling it as a constant. Otherwise, technically speaking, if you want to be very accurate, it is independent of x and t. Okay. And these kind of equations are called eigenvalue equation. Okay. Now, what is this idea about eigen? Do you know the meaning of the word eigen? Anybody? I was in Switzerland for quite some time, so I know a little bit of German and French. So this eigen stands for the German, is the German word for characteristic. Okay. So whenever I'm telling, whenever you see in textbook or anywhere, eigen equation, that means characteristic equation. Okay. So this is an eigen value, that means characteristic value. This is a eigen is nothing other than a German word for characteristic. So this is energy eigenvalue. Okay, the reason why eigen has come into English is because quantum mechanics was discovered by the German people. So, all right, so once we have this, so let us equate the left hand side with E, right hand side with E, as simple as that. So time dependence will essentially lead out to this. Okay, I have just copied this. देखो यहाँ पर I है ना, यहाँ पर -1, that means I squared, so that essentially becomes 1 upon I. Very simple. I mean, in case you find it difficult now, in your, I mean, after this class, you go through these derivations, it will become very clear. Okay, so from here, the interesting part is, if you solve this relation, you will essentially get that the influence of time, okay, the time dependence is essentially, where does it come into the picture? As an exponential, as the power of an exponential with an imaginary part. So that means, what is this? Time influences only the phase, not the amplitude. Let's get back to our original equation. E to the power of I omega t plus kx. That was the phase part, isn't it? So time influences only the phase, not the amplitude. So that means, this is a very, very crucial understanding here. It means simply that if you are essentially having any phenomenon, okay, whether it is quantum mechanics, solid state, semiconductor devices, VLSI circuits, आप कुछ भी बना लो, i7 processor, i11, i9 processor, okay, no matter how complicated the circuit, the dependence of time simply influences the phase. So that means the probability of appearance of a particle, that will depend only on the amplitude, right? Tau 0. Huh? That means the probability that a particle appears in a device, the probability that particle appears in a device and that particle starts moving and gives you current, and that current is essentially helping you to run your iPhone. Okay, so everything is essentially governed by the space dependence and independent of the time dependence. This is a very, very fundamental understanding. So that means, no matter how long you work on your iPhone, how long you work on your tablet or your smartphone or your laptop, the same does influence the probability of occupancy or the current and all that is not dependent on the time. Okay? The appearance of a particle depends only on the space variable, that is x. So if we equate the x dependence with E, so we essentially get this equation. So that essentially gives you the time independent form of Schrodinger equation, which we will deal with in the next class. And this is the equation, fundamental equation, which will essentially give you solid state itself, okay, energy bands itself. Okay, so any questions, anyone until now? Please switch on your microphone and ask questions. Let me see any chats here. Okay. Any questions, anyone until now? Hello. We have just done the very basic like +2 level mathematics until now. Okay. We will not go into any further details. Henceforth, we will be basically concerned with this equation only. So in the interview, if somebody you are using the time independent form of Schrodinger equation, why aren't you using the time dependence? Now you will be able to answer that question. Okay. Is it fine? Hello?
Yes, sir.
Yeah, okay, good. In the next class, we will go into the probability current density, because this probability current density will essentially help us understand current conduction. But I think it is already too deep for you. So, and this is the first lecture. Usually the professors don't begin the classes in the first lecture itself. But anyway, I am a bad professor in this regard. So what I shall do is, yeah, somebody wrote something. Let me just check.
Sir,
Yeah.
sir, can you open the sheet? Actually, probability of locating the quantum particle, how did you write as A square, sir?
That is A is the amplitude. Okay.
Okay.
Amplitude. So if we are doing the square of it, we will essentially find the intensity of the wave. Correct? So the intensity of the wave function in quantum mechanics gives you the probability that the particle exists in this particular location. We will understand this as we go along. In the next class, we will begin with the probability current density, and thereafter we will start with application of Schrdinger equation. Okay, three-part equation. Finally, we will culminate into this part, where we will see the formation of the energy bands. Okay, so
Okay.
our objective is to find energy bands. Kya hai? For example, it is when we say that it is conduction band, valence band. Valence band is full of electrons. How can you say the valence band is full of electrons? That means in the valence band, you will always have a very high probability of finding that electron. In the conduction band, you will have a very, very low probability of finding the electron. This high and low concept, whatever I am telling in the textbooks, we will understand it through quantum mechanics, so that we can get a perfect mathematical or modeling approach about the situations, whatever we are going along. Okay, and in the next class, so tomorrow is a holiday, I think, right? Saturday there is a class, isn't it? Oh, I don't remember the.
Yes, sir.
It's a Saturday.
Yes. So on Saturday, what we will do is we will go into a very, very interesting part that is called forces of nature. Okay, forces of nature and the various scales of observation. Okay, that is very, very crucial for your understanding at the very beginning. Usually I start with that topic itself, but I thought I will begin with quantum mechanics, and probably on Saturday we will understand, like, whatever we are dealing with in today's lecture, why don't we observe anything like this in our practical life? Okay, all this happens at the atomic scale, isn't it? So does it mean that quantum mechanics is not valid when we are speaking about that the earth is revolving around the sun, or the moon is revolving around the earth? Isn't quantum mechanics valid over there? The answer to that question is that actually quantum mechanics is valid there also, but you won't observe any probability or something over there. Why not? We will understand that in our next on Saturday, when we will be essentially dealing with the range of observation, the scales. जैसे कि हम कहते हैं ना nanometer scale. When we say, okay, something is in nanometers, whereas when we are dealing with distances, we say light years. So basically, when what is light year? It's a, I mean, probably the largest unit of length we can think of. The smallest unit of length, atometers or something. Okay, so now the point is, from the very small to the largest dimensions, whatever scientists have been able to find out, okay, in this huge range from nanometers to light years. Okay, so you will have different forces which will be applicable. All right, so for example, this discussion which we will be taking care in the next lecture, I will not go into any mathematics. I will from physics, and that is going to be very, very fundamental, and it is going to make you open your eyes. You will actually find an understanding. For example, what is the weight of the ceiling above your head? All of you are sitting in a room, right? What is the weight of the ceiling above your head? Estimate. Just guess the kilos, tons. Hello? How much should that be? Few tons, right? Definitely. Hello? Am I audible?
Yes, sir.
Yes,
Yeah,
sir. It's about.
it will be above few tons, right? I mean, if you are in the ground floor and there are, let us say, 50 floors above you, it will be like 100 tons and all. Okay. Then how come this 100-ton building is not falling on your head? Why isn't a 100-ton building is not falling above your head? Did you ever observe this? Think about it. But strangely, if there is a small earthquake, okay, let us talk about the Twin Towers. The Twin Towers were so huge, right? 9/11. Okay. This is September. So on 11th, that will be 9/11 will be Saturday, I guess. Yeah, okay, exactly. So on 9/11, in the next class, we will discuss this. So on 9/11, we remember that the flights bombarded on the Twin Towers, right? Now the question is, those Twin Towers, they were standing upright for several years without any problem. But the moment it got hit with the aeroplane, there is some conspiracy theory that they on their own, whatever it is. But with the slightest change, slightest variation, slightest kind of default in the structure, the slightest fault in the structure, what happens? The entire Twin Towers collapse like anything. So tons and tons of mortar, tons and tons of cement will just fall like anything. So my fundamental question is, why is that entire Twin Tower crumbling down like anything? You have all seen those videos on YouTube or on the television, right? How is it happening? Because you will say because of gravity. Cool. Then with the slightest fault in their construction beams and all that, the entire tons of mortar, tons of construction, right? It just collapsed like anything. But before that, the tons of in that structure was still standing upright for so many years, but it did not fall down. Twin Tower तो काफी ज़्यादा बड़ा हो गया, छोड़ो. Like if you are in a 5-story building, your ceiling above your head is weighing like 10-20 tons, but it doesn't fall on your head. But with the slight earthquake, you have seen big flyovers also fall down. Gravity does its job. Okay. But why isn't gravity working when there is no earthquake? That is my fundamental question. And this fundamental question will be answered in our next lecture. Okay? This will be very interesting. And I am not going into any physics over there. We will introduce the concept of forces and their ranges. Okay. So every force has got a particular range where it can operate. Okay. So, and that will essentially give you an idea why subatomic particles behave in a completely different realm. Why atomic particles will behave as if there is no gravity at all. In fact, in the next class, you will understand why matter exists in the 3 different stages. We all know, right? Ice is solid, water is liquid, water vapor is gas. Cool. In class 7 and class 6, we knew this. In the next class, we will understand why matter will exist in these 3 forms. What makes the difference that one particular element will exist as a solid, some other element will exist as a liquid, some other element will exist as a gas. Okay? Understand only through physics, no mathematics involved. But these are very fundamental. This will be useful if you want to go in the technical line. Okay, thank you so much for today. Although this lab is supposed to be of 2 hours, but this is I took as a lecture, so I have taken only 1 hour. On Saturday, in the next lecture, we will understand forces and their ranges, and then we will go into the probability current density. And after that, we will straight away plunge into applications of Schrodinger equation. Okay, that's all for today. Thank you. Any questions, anyone? I'll just stop recording.